So in section 8.1, we're still going to be working with normal distributions, okay? And the means and all that good stuff, finding probabilities, just like we did, normal CDF in chapter 7. What is different this time is that instead of just picking one person out of our population and saying, hey, what's the probability that this one person is in this region of our normal distribution, we're going to take a sample of people. We might not just pick one person, we're going to pick 3 or 4 or 10 or whatever. And we want to know the probability that the average of those people is in that specific reason, okay? Or in that specific region, excuse me. All right, so let's look at a couple of vocabulary type items. First one is sampling distribution of a statistic. Okay, what this is saying is that if we have a population, okay, with a whole group of people, and maybe we only pick a few. So maybe there's, 25 people in a class, and maybe we know, the height of all 25 of those people. But if I just pick 5 people, so I'm not picking everyone, okay, but I just pick 5 of those people. Those 5 people in my sample, I could take the average of just their heights, or the standard deviation of just their heights, okay? So that mean or that standard deviation, whatever statistic you're calculating, from just your sample is called a sampling distribution, okay? And the one that is particularly helpful is going to be the sampling distribution of your sample mean, okay? So that is still a mean, okay? It's an X bar because it comes from a sample, but notice that we are going to be comparing the mean of that little sample to the mean of the entire population, okay? We are going to assume for this section here in 8.1 that all of our samples are done with replacement. In other words, you draw one person, you put them back in, and they are available to be drawn again, okay? All right, so let's look at an example here. The assets in billions of dollars, so how much money they have, of the 3 wealthiest people in the U.S., Bill Gates, Amancio Ortega, and Warren Buffett. Okay, now notice this was in May 2016, so it may be different now, but we're assuming that it's still those 3 people. So our population is 3, okay, N is 3. What we're going to do is we are going to take samples of 2. So I'm going to reach in, I'm going to draw a name, and maybe I give Bill Gates for the first name. Then I put him back, and I draw a second one. And maybe I get him again, okay? So in that case, my sample would be 75 for both. I happen to get him on both draws. The mean of my sample is 75, and the probability of me getting that particular sample is 1 out of 9, okay? Or maybe my first draw is Bill Gates, and my second draw is Amancio Ortega, in which case my 2 numbers are 75 and 67. The mean of those 2 is 71. And the probability of getting that particular combination is 1/9. And I go through and I find all my different combinations. Because there are 3 people, and I could draw each of them 2 times each even, there are 9 different scenarios that could happen. I could get Bill Gates twice. I could get Bill Gates and Amancio. I could get Bill Gates and Warren Buffett. I could get Amancio twice, Amancio and then Bill Gates, Amancio and then Warren Buffett. I could get Warren Buffett twice, Warren Buffett and Bill Gates, Warren Buffett and Amancio. Notice how each time this is the mean that comes out, and because it's 1 out of 9 scenarios, the probability is 1/9. Okay, now here's what happens. How many times, if you look at the means, the different combinations of samples that I could get, 61 got mentioned 1 time. Only 1 time did the mean work out to be 61. So the probability of that is 1/9. 64 happened a couple of times. There's a 64 and there's a 64. So 64 happened twice. The probability that when you get your sample of 2 people that the mean is going to be 64 is 2/9. 67 happened only 1 time. 68 happened twice. 71 happened twice. And 79 happened once. Okay? All right, so here's what happens. If I made a distribution of this, like a bar graph, okay, my numbers would be 61, 64, 67, 68, that should be a little bit closer, 71, 75. Okay, and then if I drew their probabilities, 1/9, 2/9, here would be my distribution. And of course I can make this as a bar graph, but I'm just going to do it this way. And if we look at that, does it seem to be bell-shaped? Okay, and the answer is no, not really. Okay, now I mean it's, maybe, not terrible, but it doesn't really seem to be really high in the middle and tapering off as gradually as we normally expect bell shapes to look. Okay, all right. The mean and standard deviation of our sampling distribution. Okay, sampling distribution are these guys. And I'm going to put it in L1 and L2. Remember, I'm going to put my data in L1. Excuse my sneeze. I'm going to put my data in L1. So stat, edit. My data's in L1, 61, 64, 67, 68, 71, 75. And I'm going to put the probabilities, and look at that. I can type 1 divided by 9. I can type a probability as a fraction. Okay. Now, when I go to stat, calc, 1var stats, because I want the mean, I'm going to tell the calculator, just like I did in 6.1, I'm going to say, hey, my data's in L1, but my frequencies, how often those different ones occurred, is in L2. Okay? And it's going to say, oh, well, for your data, the mean is 67.66. I'm going to call that 67.7 if I round to the nearest tenth. And your standard deviation is going to be 4.05. Okay. Now notice, this happens when I draw samples of 2. I didn't just pick one person out of our 3-person group, our 3-person population. I picked 2. And when I picked 2 people, the mean was 67.7 and the standard deviation was 4.05. That's the average between the 2 people that I picked. Okay? All right. What if I only used the original population? Not the sampling distribution when I did groups of 2, but the original population. Okay? That is back up here. Just our 3 guys. Okay? So, oops, keep hitting the wrong thing. Stats, what I mean to push. Stat, edit. And I'm just going to say, hey, my 3 numbers were 75, 67, 61. Just those 3 numbers. What is the mean and standard deviation of just those 3 numbers? So I'm going to use L1 to tell if that's where my numbers are. I'm not putting anything in L2 because I just want the mean and standard deviation of that 3-person population. Notice it says that the mean is still 67.7, exactly the same mean. 67.7 is the mean of the 3 people. So it didn't matter whether I was finding the mean of just the 3 people or the mean of, hey, what if I drew samples of 2? The mean is still the same. But notice that the standard deviation is different. The standard deviation is the 5.73. Okay. So here's what happens. When we do samples, okay, the mean will be the same from your samples as it is from your initial population. Now notice the notation here. They put mu of x bar. That means the average from your samples. It is the same as just regular mu, the average of just your population. They're the same. The standard deviation from your samples, the little x bar is telling us it came from samples, was not the same as the standard deviation from the whole population. Okay? Specifically, mean of samples is equal to mean of population. The mean of our samples, the little x bar one, is the same as the mean of the whole population. But the mean of our standard deviation is smaller. I'm sorry, not the mean of the standard deviation. The standard deviation of the samples is smaller. Okay. Now, here's what's happening. I'm going to kind of fast forward a page or so in the notes because I want to kind of plant a seed for you to show you what's happening. This wider curve, that's a little bit shorter, is our population. This may be what your population looks like. But when you take samples, your curve is going to get taller and skinnier. Okay? So notice what happens. Let's say, I had 100 people. 100 of the richest people were in my population. And I had a distribution of them. I could say, oh, look, most people were middle. There were some that were super rich, some that were only a little bit rich, but that might be my whole population. When I take samples, if I just take this little group or that little group or that little group, okay, what will happen is sometimes in my samples I'm going to get some of the super rich. Sometimes I might get one that's less rich. Sometimes I'm going to get one in the middle. So when I average those numbers together for my samples, the mean is going to come out the same place as the mean of the whole population did. But my standard deviation will be smaller. The graph is going to get tall and skinny because I don't have, it's not going to be all low-end people or all high-end people. It's going to be a mix. So the graph will be tall and skinny. Okay? Now here's something that is interesting. Back over here, when I calculated the standard deviation, okay, the means are the same. The standard deviation should be very close to the population standard deviation divided by the square root of the sample size. And our sample size in this case was 2, because we only had 2 people in our sample. So let's see what 5.73 divided by square root of 2 works out to be. And look at that. It comes out to be 4.05. So in theory, instead of actually doing these calculations in this table and typing them into L1 and L2 and doing all that, what I could have done is found my mean and standard deviation of the whole population, know that when my sample size is 2, the mean will be the same, but I could have just taken the standard deviation and divided by square root of 2, because that's the size of my sample, and that should have been my standard deviation of my sample group. Okay? All right, so hopefully that will kind of help you get going here. I'll make a part 2 video where we work some example questions right over here.